All right, in this video, we finish up our discussion on calculating the bias of estimators of a parameter. Now, this example is going to be a two-panel one, so this panel and the next one. And it's kind of computationally involved. And so I'm going to sort of step you through it, and hopefully you can see everything sufficiently well. What I might suggest is you listen to me talk through this first panel, then you pause it, copy it down, and then listen to me talk through it a second time. Because this is a pretty important example that answers a question that I've been delaying for quite a while. So I've got x1 up through xn independently and identically distributed random variables from a distribution with an unknown variance, though I do know the variance is finite. And we're looking to figure out an unbiased estimator for that variance, sigma squared, okay? Now, we're just going to guess at an unbiased estimator and then check its bias to see if we're correct, okay? So we're going to guess and check. So by the plug-in principle, which if you remember said, if you're trying to estimate a parameter, use the function of the data that most closely mimics that parameter. So we're going to guess as our estimator 1 over n times the sum of xi minus x bar squared. X bar would be the sample mean of the x1 up through the xn, okay? So that appears to mimic the definition of variance. So let's guess that that's our estimator. And we hope it's unbiased, okay? So I'm now going to calculate the bias of that estimator, and it's going to involve some fancy algebraic and probability footwork, a little bit of fancy footwork, okay? Okay, so the first bit of algebraic fancy footwork is to note a really useful way that we can split up an xi minus an x bar squared, summed over 1 through n. So the formula is that sum can be split into the sum of the xi squared minus n copies of the square of x bar, okay? It's kind of nice. Now, I'm not going to prove it in general, but I'm going to prove the n equals 3 case. I'm going to walk us through the n equals 3 case right here, okay? So if I only had a random sample of 3, x1, x2, and x3, I'm going to prove this result. So the left-hand side is x1 minus x bar squared plus x2 minus x bar squared plus x3 minus x bar squared, okay? That's the left-hand side. I'm going to transform it into the right-hand side. So the first thing I'm going to do is I'm going to FOIL out all 3 of these. And you will note that the start is x1 squared, the start of the second guy would be x2 squared, and the start of the third guy would be x3 squared. So there they are, x1, x2, and x3 all squared, okay? They would each end with x bar squared, an x bar squared, and an x bar squared, all of them negative. So they would all end, oh, sorry, all of them positive, right? I'm sorry. Negative x bar times itself would be positive x bar squared. So it'd have 3 of these x bar squareds, positive, okay? Now the middle term in each of these is negative 2 x bar x1, negative 2 x bar x2, negative 2 x bar x3, if you FOIL them out. So there's the negative 2 x bars factored out of the x1 plus x2 plus x3. So there I FOILed all 3 out and sort of grouped them. Now, you'll note that x1 plus x2 plus x3, if I would divide that by 3, it'd be x bar. If I don't divide it by 3, it's 3 copies of x bar. So I've got the sum of the xi squareds, negative minus 2x bar times that 3x bar plus 3 of the x bars. Well, this is negative 6 of the x bar squared, and negative 6 copies of them and positive 3 copies of them leave behind a negative 3 copies of the x bar squareds. And that's exactly the formula over here when n is 3. Okay? All right, so we're going to use that result. Okay, so let's get into it. I want the expected value of my estimator, 1 over n times the sum of the xi minus the x bar squareds, okay? I can drag the 1 over n out in front. I can replace that sum with that formula I talked about up there. So there it is. And then since everything is addition or subtraction, I could push my expected value through. So I push my expected value through that summation. So it sits next to each xi squared. and I push my expected value through, drag the n out, and then I've got that x bar squared's expected value. Okay, so I push the expected value of x bar, I push the expected value through addition and subtraction. All right, now this next step from here to here requires some probability. So that's what I'm portraying down here. By definition, the variance of x is beta squared. And by definition, it's e of x squared minus e of x quantity squared. So I can solve this for e of x squared. If I solve for e of x squared, I'm going to add that e of x quantity squared over to the sigma squared. So e of x squared is sigma squared plus e of x quantity squared. So that e of xi squared, I'm going to replace it with sigma squared plus e of xi quantity squared. And that's what happens right there. This e of xi squared got replaced with this sigma squared plus e of xi quantity squared. Okay. Now, we know the variance of x bar, the variance of the sample mean, is the variance of each x divided by n. We've done that computation a lot in this class. Variance, the formula for it is the variance of x bar's formula would be e of x bar squared minus e of x bar quantity squared. There's that same right-hand side as the line above it. And if I solve for e of x bar squared, I'm just going to take this e of x bar quantity squared to the other side. So this e of x bar squared is going to get replaced by sigma squared over n plus e of x bar quantity squared. That's what happens right there. So that's how I made the move from this line to this line. Okay. All right. So then I can just simplify things. The expected value of each xi is whatever the mean is. I called it mu. So there's a mu squared. E of x bar is just a mu. The expected value of the sample mean is also just a mu. So e of x bar squared is mu squared. It's right there. And then I ran the n at the negative n through those parentheses. This sum is over n things. So there's n copies of sigma squared. There's n copies of mu squared minus the sigma squared minus an n mu squared. So the n mu squareds cancel. And I have n minus 1 copies of sigma squared, the 1 over n out in front. So I get n minus 1 divided by n times sigma squared. So the upshot of all of this is the expected value of my estimator is n minus 1 divided by n times sigma squared. So now pause it, copy it down, go back and listen to it again. I'm going to summarize this example on the next panel. Okay. So pause, copy, play. So what we showed in that last panel was the expected value of this guess for an estimator of sigma squared was n minus 1 divided by n times sigma squared. That expected value wasn't just sigma squared like I hoped. So I've got a biased estimator of sigma squared. Shoot, I'd really like an unbiased estimator. My initial guess, the expected value was a constant multiple of sigma squared, which is good news. So now I can take a second guess at an estimator of sigma squared. So my new guess is going to be, let's take the constant n over n minus 1 times my first guess, sigma squared half. My first guess was 1 over n times that sum. So now I'm sticking an n over an n minus 1 out in front of it. The n's cancel, you'll note, and I now have this for my next guess for an estimator of sigma squared, which is hopefully unbiased. And this should look familiar, right? This is what we defined as our sample variance. And this is what I held off in explaining why n minus 1 instead of n. But let's just see if this works. Here's my second guess for an unbiased estimator for sigma squared. Let's call it s squared because we did before. Let's check that it's unbiased. So I'm going to take its expected value Now, by definition, S squared was n over n minus 1 times my first guess for an estimator. I can drag the n over n minus 1 out in front of the expected value. And this expected value is what we spent a lot of time on that last panel computing. So there's my n over n minus 1 out in front, and there's the expected value from the last panel. And you'll note the n's cancel, the n minus 1's cancel, and I get sigma squared. So hey, I've got a new estimator for sigma squared that I've just proven is unbiased, okay? So that's why we had an n minus 1 in the denominator instead of an n. I wanted an unbiased estimator of the variance. And the plug-in principle, the obvious choice, turned out to be biased, okay? All right, so that's how we're going to define our sample variance. It's a great unbiased estimator, and then the square root is obviously the sample deviation or the sample error, okay? Sorry, standard deviation or sample error. All right, so that clears up a long-standing mystery. All right, one last quick panel to finish this thing off. Okay, so pause, copy, play. So finishing up the bias discussion, there's some warnings that we sort of illustrated here. Sometimes unbiased estimators don't make a lot of intuitive sense, right? Like, why did we use 1 over n minus 1 back in chapter 2 instead of 1 over n? Didn't make intuitive sense, but now we know it created an unbiased estimator versus a biased estimator for the variance. Second warning, if you've got an unbiased estimator of theta, and then you have some function, if you plug theta, the unbiased estimator, into the function, that doesn't necessarily mean it's still an unbiased estimator of theta plugged into the function. Theta plugged into the function. Okay. So a function of an unbiased estimator isn't necessarily still an unbiased estimator. Okay. But good news, if that function is a linear function, then h of theta hat is an unbiased estimator of h of theta. So linear functions don't mess up being unbiased. Like if you start squaring or square rooting, you might mess up your unbiased estimator if you push it through. All right, and then sometimes we just get lazy, okay? So if our sample sizes are getting pretty large, this unbiased thing, it might not matter. So for example, if I took that original estimator of the original guess for the estimator of the variance, then it might be good enough. So what do I mean by good enough? If I take the expected value of that initial guess for the variance estimator and then let n go to infinity, the expected value of that estimator was n minus 1 over n times sigma squared. But as n goes to infinity, n minus 1 divided by n, by L'Hopital's rule, goes to 1. So I get sigma squared. So that original estimator, as n gets really, really large, it's essentially unbiased. And we call it asymptotically unbiased estimator. Okay, asymptotic just means as we go to the infinite. Okay. Similarly, when we were trying to estimate the value of theta in a uniform distribution from 0 to theta, the MLE said, hey, use the maximum of x1 through xn. And as n goes to infinity, the expected value of that estimator is the limit as n goes to infinity of n over n plus 1 times theta. And again, n over n plus 1, as n goes to infinity, the L'Hopital is just 1. So sometimes if you got a really large sample, being slightly biased doesn't much matter, okay? All right, so this is the conclusion for the bias discussion. Now we'll move on to the other ways that we can compare estimators.